Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can loosen their grip and curiosity is allowed to drift gently without any pressure to reach a conclusion. Tonight's journey will take us into a realm that is both invisible and strangely intimate, a layer of reality that shapes everything you touch, see, and are made of, yet stubbornly refuses to behave the way common sense expects. We're going to wander, slowly and calmly, into the quantum world. Before we begin, take a moment to settle in. Maybe you're lying in bed, or sitting somewhere familiar, listening with one ear while the rest of the world fades slightly into the background. If you find these quiet explorations comforting, you're always welcome to like or subscribe, but only if it feels right. And if you're still awake enough to type, I'd love to know where in the world you're listening from and what time it is for you right now. It's a small reminder that this strange journey into physics is shared by many quiet minds, scattered across the planet, each in their own pocket of night. Now as you rest there, notice how solid everything feels. The surface beneath you supports your weight. The air around you seems calm and continuous. Light behaves predictably, bouncing off objects, carrying colours into your eyes. This is the world we trust. A world that feels stable, dependable, and most of the time, comfortably boring. For centuries, science reinforced this feeling. From the motions of planets to the arc of a thrown stone, the universe appeared to run like a finely crafted clock. If you knew the starting position of every piece and how fast each one was moving, you could, at least in principle, predict the future with perfect accuracy. This view of reality, shaped by thinkers like Isaac Newton, gave us a universe that was solid, mechanical, and deeply reassuring. Nothing mysterious. Nothing hiding behind the curtain. But early in the 20th century, something quietly unsettling began to emerge. It didn't announce itself with explosions or dramatic headlines. It appeared instead as small experimental oddities, tiny discrepancies, patterns that refused to line up with expectations. At first, these quirks were easy to ignore. Surely the instruments needed refinement. Surely the theory needed a small adjustment. What scientists eventually realized was far more profound. The problem was not the measurements. The problem was the picture of reality itself. At very small scales, the universe does not behave like a clock. It does not move smoothly from one moment to the next, carrying definite properties the way everyday objects do. Instead, it behaves like something far more elusive, something that spreads out, overlaps with itself, and only settles into a definite outcome when we look closely enough to ask a very specific question. This is where quantum mechanics enters the story, not as a replacement for the everyday world you live in, but as a deeper layer beneath it, a layer that works astonishingly well, predicting experimental outcomes with accuracy so precise that it has become the most successful scientific framework ever created. And yet at the same time, it leaves us deeply uncomfortable when we try to explain what it means. Tonight, we are not here to wrestle with equations or memorize technical language. We are here to follow the logic of the experiments themselves, to see how careful observation led scientists step by step away from a world of certainty and into a world of probabilities, a world where particles behave like waves, where outcomes are not fixed until measured, and where distant objects can share connections that defy our everyday sense of separation. If that sounds unsettling, that's perfectly normal. Even the people who built quantum mechanics felt that way. Many of them spent the rest of their lives debating what their own equations were telling them about reality. Some were content to accept the predictions and stop there. Others insisted that understanding what is really going on still matters, even if the answer challenges everything we think we know. As we begin, it helps to remember one gentle reassurance. Quantum mechanics does not make the world chaotic or meaningless. It does not say that anything can happen or that reality is arbitrary. What it tells us is subtler than that. It tells us that nature is consistent, but not in the way our intuition evolved to expect. It speaks in the language of likelihoods rather than certainties, of patterns rather than paths. To understand how we arrived at such a strange conclusion, we start not with particles or equations, but with something much more familiar: waves. Waves are everywhere in your life. You hear them as sound, feel them as vibrations, and see them in the gentle ripples spreading across water. A wave is not a thing that travels from one place to another in the way a pebble does. It is a pattern, a coordinated motion that spreads out through space. When waves meet, they combine. Sometimes they reinforce each other, creating something stronger. Sometimes they cancel, leaving behind surprising gaps of calm. These simple properties, so easy to observe in water or sound, turn out to leave unmistakable signatures. And one of those signatures, a delicate pattern of alternating presence and absence, will become the first crack in the solid-looking surface of classical reality. In a moment, we'll let that idea settle in gently. We'll look at how waves announce themselves and why their patterns are so distinctive that they cannot be mistaken for anything else. There's no rush, no test at the end, just a slow unfolding of an idea that, once seen, cannot be unseen. For now, allow yourself to rest in this quiet tension between the world as it feels and the world as it truly behaves beneath the surface. A universe that works flawlessly, yet refuses to sit still long enough to be pinned down by certainty. A reality that, when examined closely, turns out to be far more fluid and far more interesting than it first appears. And with that soft question lingering in the background, we can begin to explore the gentle language of waves and the subtle patterns that hint at something deeper, waiting just out of sight. Before anything in this story becomes puzzling, it helps to spend a little time with something deeply familiar, something so ordinary that we rarely stop to think about it. Waves. As you rest there, perhaps listening through one ear while the other drifts towards sleep, you are already surrounded by waves. Sound reaches you as gentle pressure patterns moving through air. Light arrives as rhythmic oscillations that your eyes quietly translate into colour and shape. Even your own breathing creates slow, repeating motions, rising and falling in a steady rhythm. A wave, at its heart, is not a travelling object. It is a pattern, a coordinated movement that spreads through space, carrying energy and information without carrying matter along for the ride. When you drop a pebble into a still pond, the water itself does not rush outward. Instead, each tiny parcel of water moves up and down, passing the motion along to its neighbours. What travels is the pattern, not the substance. This distinction turns out to matter more than it first appears. One of the most important features of waves is how they behave when they meet. Unlike solid objects which collide and bounce apart, waves overlap. They pass through one another, combining their motions in a process that feels almost polite. Where two wave peaks meet, they add together, creating a larger peak. Where a peak meets a trough, they cancel, leaving behind a moment of surprising calm. This process is called interference, though you can think of it simply as cooperation and cancellation. It happens whether the waves are made of water, air, or light. The details change, but the underlying behaviour remains the same, and this behaviour leaves behind a very distinctive signature. Imagine standing at the edge of a quiet lake. You toss two pebbles into the water, a short distance apart. Each pebble sends out its own circular ripples. As those ripples expand, they begin to overlap. In some places, the crests of the waves arrive together, amplifying one another. In other places, a crest meets a trough, flattening the surface instead. What you see is not chaos, but an intricate pattern of alternating regions, lively bands of motion followed by calmer gaps. That pattern is not random. It is structured, repeatable, and unmistakable. Once you've seen it, you know you are looking at waves. Light behaves in much the same way. When beams of light overlap, they interfere. Under the right conditions, they produce bright regions where the light intensifies, and dark regions where it nearly vanishes. These alternating bands of brightness and darkness are not shadows or obstructions. They are the result of waves adding and subtracting from one another with exquisite precision. For a long time, this was one of the strongest arguments that light must be a wave. No particle picture could naturally explain why light would cancel itself in some places and reinforce itself in others. Waves, on the other hand, do this effortlessly. So far, everything feels safe, comforting even. Waves behave like waves should. They spread, they overlap, they interfere. There's no mystery here, only elegant geometry written in motion. Now imagine narrowing this behaviour down into something even simpler. Instead of ripples on water, picture a stream of waves travelling toward a thin barrier with a narrow opening. As the waves pass through that opening, they spread out on the other side. This spreading is called diffraction, though you can think of it as the wave losing its sense of direction, fanning out as soon as it's no longer constrained. If you place a screen behind the opening and allow the waves to strike it, you will not see a sharp image of the opening. Instead, you will see a broad, smooth distribution. The wave has spread itself out, distributing its energy across space. Now add a second opening next to the first. As the waves pass through both openings, each opening becomes a new source of spreading waves. Those waves overlap, and interference appears. Bright regions where the waves reinforce, dark regions where they cancel. The screen fills with a repeating pattern of bands, a visual fingerprint that announces without ambiguity that waves are at work. This setup, simple as it sounds, will soon become one of the most important experiments in the history of science. But for now, we stay with a familiar version. Water waves, light waves, patterns that emerge not from collisions but from cooperation. What makes these patterns so compelling is their inevitability. You cannot tune them away. You cannot persuade waves to behave otherwise. If waves can pass through two openings and overlap, interference will appear. It is not optional. It is not a special case. It is the natural consequence of how waves exist in space. And this inevitability is what makes the next step so unsettling. Because if interference is the signature of waves, then seeing interference tells you something very specific about what you're observing. It tells you that whatever produced the pattern must have been spread out. It must have passed through both openings at once, overlapping with itself in a way no classical object ever could. At least, that is what common sense insists. At this stage of the story, no one is nervous. The mathematics matches the experiments. The pictures match intuition. Waves do what waves do, and the universe remains comfortably understandable. But notice something quietly important. Nothing in this description relies on size. Waves do not care whether they are large or small. The principles that govern ripples on a pond also govern light crossing a laboratory. The scale changes, but the logic does not. This universality will matter later. For now, let the image of those gentle bands linger. Bright, dark, bright, dark. A steady rhythm etched into space by nothing more than overlapping patterns. No decisions, no surprises, just the quiet, reliable language of waves speaking for itself. As this picture settles, we're ready for a comparison that feels almost too obvious to be interesting. We will take the same setup, the same openings, the same screen, and ask what happens when we replace waves with something solid, something unmistakably object-like, something that carries no ambiguity about where it is or where it goes. The answer will feel reassuring at first, and then, very soon, profoundly insufficient, but there is no need to rush there just yet. For the moment, rest with the idea that waves leave signatures, clear, structured, undeniable signatures, and that these signatures do not belong to particles, bullets, or grains of sand. At least, not according to everything we have ever learned about the everyday world. And with that quiet distinction in place, the story naturally drifts toward the comparison that will begin to loosen the foundations beneath our feet. Now that the gentle behaviour of waves has had time to settle, we can let the picture become slightly more precise without making it any heavier. This setup we're about to explore is simple enough to describe in a sentence, yet subtle enough to quietly reshape how we think about the world. Imagine a steady stream of waves moving toward a thin barrier. The barrier blocks the waves everywhere except for a narrow opening. Beyond that opening sits a flat screen, patiently waiting to record whatever arrives. When the waves pass through a single narrow opening, something very predictable happens. The opening acts like a new starting point. The waves spread out on the other side, fanning gently across space. By the time they reach the screen, they form a smooth, rounded distribution. The centre is the brightest, and it gradually fades toward the edges, like a soft glow that loses intensity as it spreads. Nothing about this feels surprising. Constrain a wave, and it resists by spreading out. This is the quiet compromise waves always make. They accept boundaries, but only temporarily. Now imagine adding a second opening, placed close to the first. The rest of the setup remains exactly the same incoming waves, the same screen, the same distance. If waves were simply passing through each opening independently, you might expect the result on the screen to be just the sum of two single opening patterns. Two smooth humps, added together, brighter in the middle, dimmer on the sides. But that is not what appears. Instead, the screen fills with a striking pattern of alternating bands, bright regions where the waves arrive together, reinforcing one another, dark regions where they arrive out of step, cancelling almost completely. The smooth glow is replaced by a rhythm, presence and absence, light and dark, again and again. This pattern is not fragile. It does not depend on fine-tuning or special tricks. As long as the waves are coherent, meaning they keep a stable rhythm with one another, the pattern appears reliably. Change the colour of the light, and the spacing of the bands shifts. Change the distance to the screen, and the pattern stretches or compresses, but the essential structure remains. Bright, dark, bright, dark. At this point in history, this behaviour was not a shock. It was expected. In fact, it became one of the most convincing demonstrations that light behaves like a wave. Long before anyone worried about quantum mechanics, experiments like this quietly confirmed that light spreads, overlaps, and interferes with itself in exactly the way waves should. So far, everything aligns neatly with intuition. Two openings create two spreading wave sources. Those waves overlap. Interference follows. The pattern is the natural outcome of geometry and timing. And it is important to notice something subtle here. The pattern does not arise because the waves choose one opening or the other. It arises because the wave is, in a meaningful sense, present at both openings at the same time. Each opening contributes to the final result, and the wave emerging from one opening knows about the wave emerging from the other, not through communication, but through overlap. This idea feels completely natural when we talk about waves. A ripple in water does not need to decide which path to take. It simply spreads wherever it can. Its presence is extended, not localized to a single point. As long as we are talking about light as a wave, nothing feels strange. But pause for a moment and let the picture become very concrete. Let the openings become extremely narrow. Let the incoming light become extremely faint, so faint that individual detections appear on the screen one at a time as tiny flashes. At first, this still seems unremarkable. Even a wave delivers its energy in small packets when detected. A dim light produces sparse hits. A bright light produces many. The underlying pattern, however, emerges only after many detections are collected. And when those individual detections are allowed to accumulate, something remarkable happens. Even though each flash appears at a single point, the collection of many flashes slowly builds the same interference pattern. Bright bands form where flashes are common. Dark bands appear where flashes are rare. The wave pattern reveals itself statistically, one tiny event at a time. This is a crucial transition. It tells us that the interference pattern is not the result of particles bumping into one another or crowding together. Each detection happens alone, and yet, taken together, they organize into a structure that belongs to waves. At this stage, physicists were still calm. Light, after all, had already shown its wave-like nature in many other contexts. The idea that individual detections could add up to a wave pattern was curious, but not alarming. What made this experiment truly transformative was not what happened with light. It was what happened when the same setup was used with objects that had always been considered particles. Electrons. Electrons were not abstract waves. They had mass. They carried electric charge. They could be deflected by magnetic fields and counted individually. They left tracks in detectors. They behaved in every practical sense like tiny objects. And yet when electrons were sent toward a barrier with two narrow openings, the screen on the other side filled with the same alternating pattern. Bright regions, dark gaps, interference. At first, some suspected that electrons were interacting with one another, somehow nudging each other into place. So the experiment was repeated with the electron source turned down until electrons passed through the setup one at a time, with long pauses in between. The result didn't change. Each electron appeared as a single, localized impact. A dot. A point. Nothing spread out. Nothing smeared across space. And yet, as these points accumulated, they traced out the same interference pattern as waves of light. This is the moment where the story begins to lean away from comfort. Because if interference is the unmistakable signature of waves, then electrons in this experiment are behaving like waves, not metaphorically, not approximately, but in the only way that matters. They produce the same pattern, and yet, when detected, each electron arrives as a single, indivisible event, not half an electron here and half there. Not a faint smear across the screen, a single dot at a definite place. Something is spreading out, something is interfering with itself, and something else is being detected as a localized object. All three of these statements are true at the same time. For now, resist the urge to resolve the tension. We're not yet asking what an electron really is, or how it can behave in such contradictory ways. We're simply noticing what the experiments insist upon. The pattern exists. It is reproducible. It does not go away when conditions are changed or simplified. And it appears precisely where classical intuition says it should not. As this realization settles, the quiet language of waves begins to speak in a context where it does not seem to belong. And once it does, the question that will guide the rest of our journey quietly takes shape. If particles can create wave patterns, then what exactly is doing the waving? With the strange pattern from electrons still quietly lingering in the background, it helps to pause and return to something deeply reassuring, something solid, something that behaves exactly the way we expect. Before questioning reality any further, we give our intuition a chance to speak clearly. Imagine a simple setup. A sturdy barrier stands in front of you with two narrow openings cut into it. Behind the barrier sits a screen, ready to record whatever passes through. This time, instead of waves or electrons, you fire tiny solid objects toward the barrier. Little pellets, marbles, bullets if you like, though we can picture something harmless and gentle for the sake of calm. Each object travels along a clear path. It moves forward, hits the barrier, and either passes through one opening or the other. There is no ambiguity about this. A marble cannot split itself. It cannot pass through both openings at once. It must choose. When the objects strike the screen, they leave marks. Each mark corresponds to a definite journey. If the marble went through the left opening, it lands in a region aligned with that opening. If it went through the right, it lands in a different region. After many marbles have passed through, the screen displays two clusters, one behind each opening, clean, predictable, comfortingly dull. There are no alternating bands, no mysterious gaps, no hints of cancellation or reinforcement. Just two piles of impacts neatly lined up with the openings that produced them. This is what classical reasoning expects, and more importantly, this is what everyday experience has trained us to expect. Objects follow paths. They occupy one place at a time. They move through space in ways that feel continuous and trackable. If we do not see an object somewhere, it is simply not there. Nothing about this picture strains the mind. You can make the marbles smaller. You can fire them faster or slower. You can space them out in time, sending one at a time with long pauses in between. The result remains unchanged. Two openings produce two clusters. No surprises emerge, no matter how patient you are. This is an important contrast, because it shows that the interference pattern we saw earlier is not an inevitable consequence of having two openings. It is not a trick of geometry. It is not a limitation of the screen or the detector. It is something specific to waves, and only waves. At least that is what logic insists. Now consider what this contrast tells us. When we use objects that behave like particles, we get particle-like results. When we use waves, we get wave-like results. The universe appears to be consistent. It responds to the nature of what we send through the openings. So when electrons produce interference, the question becomes unavoidable. In what sense are electrons behaving like waves, and in what sense are they behaving like particles? The classical picture offers no room for compromise. An object must be one or the other. It must either follow a path like a marble, or spread out like a wave. There is no third option. And yet, the experiments force us into exactly that uncomfortable middle ground. An electron, when detected, behaves like a marble. It arrives at a single point. It leaves a single mark. It does not smear itself across the screen. But in between the source and the screen, something about its behavior produces the same pattern we associate with waves. This is where many people instinctively reach for hidden explanations. Perhaps the electron really does go through one opening, but is subtly deflected by some unknown force. Perhaps the barrier itself somehow nudges electrons into preferred landing spots. Perhaps there is a secret mechanism at work guiding each electron to its place. These ideas are natural. They try to preserve the comforting picture of particles following definite paths. But careful experiments rule them out, one by one. Change the spacing between the openings, and the pattern shifts in a way that depends on both openings being available. Block one opening, and the interference disappears entirely. Restore it, and the pattern returns. The electron's behavior depends on the presence of both openings, even though it is detected as a single object. To make the puzzle sharper, physicists asked a simple question. What if we watch the electron as it passes through the barrier? What if we place a detector at the openings and check which one the electron uses? When this is done, the interference pattern vanishes. The screen now shows two clusters, just like the marbles. The moment the electron is forced to behave like a path-following object, it does so, and the wave-like pattern disappears. This result is deeply unsettling, but we will explore its meaning more gently later. For now, notice the pattern. When we treat the electron like a particle, it behaves like one. When we do not ask which path it takes, it behaves like something spread out. The universe seems to be responding not only to physical arrangements, but to the type of questions we ask. At this point, it becomes clear why the classical picture cannot survive intact. Classical physics assumes that objects always possess definite properties, whether we measure them or not. A marble always has a position. A bullet always follows a trajectory. Measurement simply reveals what was already there. Quantum experiments refuse to cooperate with this assumption. The electron does not behave like a tiny marble with a hidden path, nor does it behave like a wave in the everyday sense. It occupies a strange middle ground, where the outcome of an experiment depends on what information is available, not just on the physical setup alone. And yet, despite all this strangeness, the result's not random chaos. The interference pattern is precise, the probabilities are stable. Run the experiment today or tomorrow, here or across the world, and the same structure appears. Nature is not confused, only our expectations are. This realization marks an important shift in the story. We're no longer dealing with a minor correction to classical thinking. We are facing a fundamental limit on how far everyday intuition can be stretched. The marble experiment reminds us what the world looks like when objects behave in familiar ways. It gives us a baseline, a reference point. Against that reference, the behavior of electrons stands out sharply, not as a small deviation, but as a categorical difference. From here on, the question is no longer whether electrons are strange. That much is settled. The real question becomes how to describe their behavior without forcing them into categories that no longer apply. To answer that, physicists introduced a new kind of description, one that does not track paths or positions directly, but instead keeps track of possibilities, likelihoods, patterns of expectation rather than definite histories. In other words, they stopped trying to follow the electron like a marble and started describing it like a probability. And that quiet shift from certainty to likelihood is where the quantum story truly begins to take shape. The contrast we just explored leaves a quiet echo behind it. Marbles behave like marbles, waves behave like waves, and electrons somehow insist on borrowing from both worlds without fully belonging to either. To make sense of this, physicists did not rush to conclusions. They slowed down. They repeated experiments. They tried to catch electrons in the act, hoping that patience would reveal a hidden simplicity. At first glance, an electron seems like the very definition of a particle. It has mass. It carries electric charge. It can be steered with magnetic fields and counted one by one. In cloud chambers, electrons leave delicate trails, like thin threads stitched into space, marking where they have been. In circuits, they flow and produce heat. In chemistry, they bind atoms together. Nothing about an electron's resume suggests a tendency to spread out like a ripple on a pond, and yet, when electrons are sent toward two narrow openings, the screen behind them fills with the same alternating pattern that waves produce. Bright regions where arrivals are common, dark regions where arrivals are rare, the same rhythm of presence and absence carved into space with quiet precision. At this stage, it is tempting to imagine that electrons are simply very small objects with very complicated paths. Perhaps each electron travels through one opening or the other, but the barrier and the environment nudge it slightly, bending its path in subtle ways. After all, in everyday life, tiny objects are more easily deflected than large ones. A breeze can move a feather, but not a stone. So physicists tested this idea carefully. They shielded the experiment from stray fields. They refined the apparatus. They removed as many sources of disturbance as possible, and still the pattern remained. Then they tried something more drastic. They reduced the number of electrons, not just a little, but dramatically. The electron source was turned down until electrons were sent through the setup one at a time, with long pauses in between, seconds, sometimes minutes, enough time that no two electrons could possibly interact with each other. If the interference pattern were caused by electrons jostling one another, it should disappear under these conditions. There would be nothing left to interfere. But that is not what happened. Each electron arrived at the screen as a single localized dot, a tiny mark, appearing without warning at a definite place. There was no visible sign of spreading, no hint of a wave washing across the screen, just a point. And yet, as these points accumulated over time, the familiar pattern emerged. Slowly, patiently, dot by dot. The same bright bands and dark gaps revealed themselves as if guided by an invisible template. This result is one of the most quietly astonishing in all of science. It tells us that the interference pattern is not built by interactions between electrons. Each electron acts alone, and yet, taken together, their behavior follows a wave-like rule. It is as if each electron consults a map before arriving, a map that assigns different likelihoods to different locations on the screen. Where the map is bright, arrivals are common. Where it is dark, arrivals are rare. Each electron chooses a single destination, but the choices are not evenly distributed. Crucially, this map does not describe what the electron is doing in the ordinary sense. It does not tell us where the electron is at each moment or which path it takes. It tells us only how likely different outcomes are if we decide to look. This is where a subtle but important shift occurs. Classical physics describes objects by tracking their properties directly. Position, speed, direction. Quantum physics, in contrast, describes systems by tracking possibilities, likelihoods, patterns of expectation. For electrons, this description works with stunning accuracy. If you calculate the probability map for the two-opening experiment, it matches the observed pattern precisely. Not approximately, not loosely, precisely. And yet the map itself is not something we can observe directly. We never see a fuzzy electron spread across space. We never detect half an electron here and half there. Every detection is sharp, definite, singular. This tension is the heart of the quantum puzzle. Something behaves like a wave, spreading out and interfering with itself. Something else behaves like a particle, arriving as a localized event. And both behaviors are tied to the same entity. To make matters even stranger, the behavior changes depending on what information is available. When we do not check which opening the electron uses, the interference pattern appears. When we place detectors to monitor the openings, forcing the electron to reveal a path, the pattern vanishes. The screen returns to two simple clusters, as if the electron has decided to behave like a marble after all. It is not that the electron senses being watched in a human way. There is no awareness or intention involved. What matters is whether the experimental setup allows path information to exist at all. If the setup makes it possible, even in principle, to know which opening the electron used, the wave-like pattern disappears. This sensitivity to information is deeply foreign to classical thinking. In the everyday world, objects do what they do regardless of whether anyone is paying attention. A thrown ball follows its trajectory whether or not someone watches it. Measurement reveals reality. It does not create it. Quantum experiments suggest a different story. At very small scales, the way reality unfolds depends on what can be known, not just on what physically happens. The electron's behaviour is not fully specified until the moment of detection. Before that, it is described only by a pattern of possibilities. This does not mean the electron is vague or poorly defined. On the contrary, the predictions are razor sharp. Run the experiment 1,000 times and the statistics will match the probability map exactly. The uncertainty lies not in the outcomes as a group, but in which outcome any single electron will choose. At this point in the story, it becomes clear why early physicists felt both triumph and discomfort. On one hand, they had discovered a framework that predicted experimental results with unprecedented precision. On the other, they had lost the comforting picture of a world made of tiny objects following hidden paths. The electron refuses to be squeezed into that picture. It is not a marble in disguise. It is not a wave made of substance. It is something else entirely, something that demands a new way of speaking about reality. Rather than asking where the electron is, quantum theory asks what can happen. Rather than tracing trajectories, it assigns likelihoods, and rather than promising certainty for individual events, it offers a remarkably reliable structure for the pattern as a whole. As unsettling as this may feel, it is also quietly elegant. The universe has not become chaotic or lawless. It has simply revealed that its laws operate at a level deeper than our everyday intuitions. With this realization in place, the next step becomes almost inevitable. If electrons are guided by patterns of possibility rather than definite paths, we need a way to describe those patterns clearly and consistently. And that need leads us gently and unavoidably toward the idea of probability waves and the strange but powerful mathematical language that captures them. There is a particular stillness that settles in when an experiment is slowed down enough, not rushed, not crowded with events, just one thing happening, then nothing, then one thing again. This quiet pace is where the behaviour of electrons becomes most revealing, not louder but clearer. Picture the experiment once more. A source releases electrons so gently that they arrive one by one, separated by long stretches of time. There is no stream, no flow, no possibility that one electron could nudge or influence another. Each event is isolated, solitary, patient. When an electron reaches the screen, it announces itself with a tiny flash, a single point, a brief moment of certainty, then silence again. At first, the screen looks empty, dotted only with a handful of scattered marks. Nothing about these early dots hints at any hidden order. They appear random, like raindrops falling on dry ground. But as time passes, something subtle begins to emerge. Certain regions of the screen receive dots more often than others. Some areas remain almost untouched. Slowly, without any coordination between electrons, the familiar pattern takes shape. Bright bands become visible where dots cluster densely. Dark gaps persist where dots are rare. This is not a metaphor. It is not an artistic interpretation. The pattern emerges objectively, statistically, as a fact of repeated observation. The same pattern that waves produce appears here, even though nothing is arriving as a wave. This is the moment when the story truly changes character. Because now we are forced to confront a strange combination of truths. Each electron is detected as a single, localized event. It never spreads itself across the screen. It never arrives in pieces. And yet, the collection of many such events follows a rule that belongs to waves. It is tempting, at this point, to imagine that the electron must be doing something wave-like while it travels, even if it looks particle-like when it arrives. But this raises an immediate question. What exactly is waving? There is no substance spreading out like water, no medium vibrating like air, nothing tangible moving smoothly through space, and yet something is clearly extended, because the outcome depends on the presence of both openings. Block one, and the pattern changes instantly. restore it, and the pattern returns. Whatever guides the electron's arrival must somehow account for both paths at once. To make sense of this, physicists introduced a new kind of description. Instead of asking where the electron is at every moment, they asked a different question. Given the setup, where is the electron likely to arrive if we look? The answer to that question is not a single point. It is a distribution, a landscape of likelihoods. Some destinations are favoured, others are suppressed. The electron does not choose freely among all possibilities. Its choices are constrained by an invisible structure that shapes the statistics of many events. You can think of this structure as a quiet map laid out across space. The map does not tell the electron where it must go. It tells us how often electrons will arrive at different places if we repeat the experiment many times. Where the map is bright, arrivals are common. Where it is dim, arrivals are rare. Importantly, this map is not an expression of ignorance. It is not a placeholder for missing information about hidden paths. It is the most complete description available. Nothing more detailed exists beneath it, at least according to everything the experiments tell us. This realization marks a decisive break from classical thinking. In the classical world, probabilities arise because we lack information. If you toss a coin and do not know its initial conditions precisely, you describe the outcome as likely heads or tails. But the coin itself follows a definite path. The uncertainty lives in your knowledge, not in the coin. With electrons, the uncertainty appears to be fundamental. Even with complete knowledge of the setup, the outcome of any single detection cannot be predicted with certainty. The best we can do is describe the pattern that emerges over many trials, and yet this uncertainty is not sloppy. It is not approximate. The probability map is precise, stable, and reproducible. Change the distance between the openings and the map reshapes itself predictably. Change the energy of the electrons and the spacing of the bands adjust accordingly. The structure responds smoothly to physical changes, even though individual outcomes remain unpredictable. This balance between unpredictability and order is one of the most remarkable features of the quantum world. Nature seems to care deeply about patterns, but not about individual stories. Each electron writes its own tiny story, arriving at a place no one could foresee. But together, they follow a script so reliable that it can be calculated to extraordinary accuracy. This way of describing reality requires a shift in how we think about cause and effect. In everyday life, causes produce specific outcomes. Throw a ball with a certain speed and angle, and it lands in a predictable place. In the quantum realm, causes shape distributions. They influence how often outcomes occur, not which outcome occurs next. This does not mean that the electron is making choices or responding to intentions. There is no decision-making involved. The behavior emerges from the structure of the description itself. The experimental setup defines the landscape of possibilities, and each detection samples from that landscape. When we resist this idea, it is usually because we are trying to force electrons into a narrative that belongs to marbles. We want them to have paths. We want them to have histories that exist whether or not we look. But the experiments simply do not support that picture. Instead, they point toward a different kind of realism. One in which the most fundamental description of nature is not a list of what is happening, but a guide to what can happen and how likely each possibility is. This perspective can feel unsettling at first. It seems to strip the world of its solidity, replacing concrete motion with abstract likelihood. But notice something important. The world you experience does not dissolve into uncertainty. Tables remain tables, chairs remain chairs. The strange behavior is confined to scales far smaller than everyday life, where patterns of probability average out into stability. For now, it is enough to sit with the idea that one electron at a time is all it takes to reveal the quantum structure of reality. No crowds, no interactions, just repetition, patience, and a willingness to let go of the expectation that the universe must tell us exactly what will happen next. As this understanding settles in, a new question quietly arises. If electrons are guided by probability maps rather than definite paths, how do we describe those maps in a precise and consistent way? What kind of language can capture something that is neither a wave of matter nor a trail of objects? The answer to that question leads us toward the idea of probability waves, a concept that will soon become central to everything that follows. There is a quiet moment in the history of science when the universe seems to hesitate, as if taking a breath before changing its mind about how it wants to be understood. For physics, that moment arrived when it became clear that the strange behaviour we'd been watching could no longer be explained as a small correction to the old picture. The clockwork universe, so reliable and comforting, had reached the limit of what it could offer. For generations, reality had been described as if it were a perfectly tuned mechanism. Objects possessed definite properties at all times. They had positions, speeds, and trajectories, whether anyone measured them or not. If predictions failed, the failure could always be blamed on missing information. Measure more carefully, calculate more precisely, and the fog would lift. But the electron experiments refused to cooperate with that hope. As we've seen, electrons did not merely hide their paths. They behaved as though paths were not the right thing to talk about in the first place. The interference pattern appeared not because electrons were confused or disturbed, but because the world itself seemed to operate according to a different set of rules at very small scales. To make sense of this, physicists took a conceptual leap that, in hindsight, marks one of the most profound shifts in scientific thinking. They stopped asking where things are, and began asking what is likely to happen. One of the key figures in this shift was Louis de Broglie, who proposed something both simple and unsettling. Perhaps the wave-like behaviour we observe is not a wave of matter at all. Perhaps it is a wave of possibility. This idea reframed the entire problem. Instead of imagining electrons as tiny objects smeared out across space, de Broglie suggested that what spreads out is not the electron itself, but a description of its potential outcomes. The wave does not tell us what the electron is doing moment by moment. It tells us how likely different results are if we choose to look. This is a subtle distinction, but it changes everything. In the classical world, waves describe physical motion. Water rises and falls. Air compresses and expands. Something tangible is always moving. In the quantum world, the wave describes something quieter and more abstract. It describes expectation. It sketches a landscape of possibilities across space. Where this landscape is high, outcomes are common. Where it dips low, outcomes are rare. And where different possibilities overlap, they can reinforce or suppress one another, creating the familiar patterns we have already encountered. This explains, in a single stroke, why interference appears even when electrons arrive one by one. Each electron does not interfere with other electrons. It interferes with the structure of possibilities laid out by the experiment itself. The pattern emerges not because electrons are colliding or coordinating, but because the underlying map of likelihood has peaks and valleys. At this point, the universe quietly stops behaving like a clock. In a clockwork world, knowing the present means knowing the future. Given enough information, uncertainty shrinks towards zero. But in this new picture, even complete knowledge of the setup does not determine the outcome of an individual event. It determines only the range of possibilities and how frequently each one will occur over time. This is not a statement about human ignorance. It is not saying that we are clumsy observers, missing crucial details. It is saying that nature itself does not assign definite outcomes in advance. The uncertainty is not in our heads, it is woven into the fabric of reality. That realization was deeply uncomfortable for many of the physicists who encountered it. Albert Einstein famously resisted it, insisting that the universe should not play dice. Others were more willing to accept the new rules, even if they could not yet explain why those rules existed. What made the situation even more challenging was how precise this probabilistic description turned out to be. The new theory did not produce vague or approximate predictions. It produced numbers that matched experiments with extraordinary accuracy. Again and again, nature confirmed that the probability-based approach was not a temporary patch, but a fundamental feature. And so, the old promise of certainty was quietly replaced by a new promise. Not that we would know exactly what will happen next, but that we could know, with remarkable reliability, how often different outcomes would occur. In many ways, this is a gentler promise. It does not demand perfection from the universe. It allows for variation, for surprise, for outcomes that cannot be foretold in advance. And yet, it preserves order at a deeper level. The patterns remain stable. The statistics repeat. The structure holds. To live with this picture, physicists had to adjust their sense of what it means to explain something. Explanation no longer meant tracing a single chain of cause and effect. It meant understanding the shape of the probability landscape and how it responds to changes in the experimental setup. Move the openings closer together, and the landscape reshapes itself. Increase the energy of the electrons and the spacing of the pattern adjusts. Block a path, and entire regions of possibility disappear. The theory responds smoothly and predictably, even though individual events remain uncertain. This shift also required a new kind of humility. It asked scientists to accept that some questions, at least in their traditional form, might not have answers. Asking which path an electron takes may be like asking which side of a ripple is the real wave. The question assumes a structure that the phenomenon itself does not possess. None of this means that the world has become vague or ill-defined. On the contrary, the probabilistic description is exact. It leaves no room for ambiguity about the overall pattern. What it refuses to provide is a detailed narrative for each individual event. This is the moment when reality stops behaving like a story with a single plot line and starts behaving like a book of possibilities, where each page is weighted differently. Some pages are read often, others are rarely opened. But the book as a whole is written with extraordinary care. As strange as this may feel, it is worth noticing how quietly natural it becomes once we stop demanding more than the theory offers. We no longer need electrons to be tiny marbles or ghostly waves of matter. We can allow them to be what the experiments insist they are, entities whose behaviour is governed by patterns of likelihood rather than predetermined paths. With this perspective in place, the next step becomes clearer. If reality is guided by a wave of possibility rather than a track of certainty, we need a way to describe that wave consistently and precisely. A language that captures how likelihood spreads, overlaps, and reshapes itself as conditions change. That language already exists. It is subtle, powerful, and often misunderstood, and it will soon bring us face to face with one of the deepest puzzles in all of physics, the moment when possibility gives way to fact. By now, the idea that has quietly taken root is this. The wave in quantum physics is not telling a story about what is happening, but about what could happen. It does not describe a moving object in space. It offers a forecast, a structured expectation, a gentle outline of possibilities waiting to become real. This distinction is subtle, but once it settles in, it changes how everything else fits together. In everyday life, descriptions usually point to facts. When we say a car is parked outside, we mean it occupies a definite place. When we say a glass is full, we're describing a physical condition that exists whether anyone looks or not. Our language evolved to track objects, not possibilities. The quantum wave asks us to use language differently. Think again of the quiet map we introduced earlier. Not a road map with fixed routes, but a weather map. One that does not tell you where a single raindrop will fall, but shows where rain is more likely, and where the sky will probably remain clear. Such a map does not describe any individual drop. It describes a pattern that emerges only when many events are considered together. This is how the quantum wave functions. It spreads across space, not as matter, but as likelihood. At every location, it assigns a weight, a sense of how often an event will occur if the experiment is repeated again and again. Where that weight is high, detections cluster. Where it is low, detections thin out. Where different regions of likelihood overlap, they combine, sometimes reinforcing one another, sometimes cancelling almost completely. This is why interference appears so naturally in quantum experiments. Interference is not the collision of particles, it is the interaction of possibilities. When two paths are available, the likelihood associated with each path spreads out and overlaps. In some places, the possibilities align, making outcomes more frequent. In other places, they oppose one another, making outcomes rare. The electron itself still arrives as a single event, but the pattern of many arrivals reflects the structure of the underlying wave of probability. At this point, it is tempting to think of the wave as merely a mathematical trick, a convenient way to calculate outcomes without saying anything real about the world. And indeed, some physicists were content to treat it exactly that way. But the wave's role is too consistent, too reliable, to be dismissed as a bookkeeping device. It responds smoothly to every change in the experimental setup. Move a barrier, and the entire landscape of likelihood reshapes itself. Adjust the energy of the electrons, and the spacing of the pattern shifts predictably. The wave behaves as though it is deeply connected to the physical arrangement of the world, even if it is not a physical object itself. This leads to an important clarification. The wave does not describe ignorance. It does not say, "We don't know what the electron is doing." It says, "There is no fact of the matter yet about which outcome will occur." That statement is stronger and more unsettling. In classical physics, probability enters only because of incomplete knowledge. If you knew every detail, uncertainty would vanish. In quantum physics, probability remains even when nothing is missing. You can prepare the same experiment with exquisite care, knowing everything that can be known, and still be unable to predict the outcome of a single event. The wave captures this reality perfectly. It does not pretend to offer certainty when none exists. It offers the most complete description possible and then stops. This is why it is so important to say that the wave predicts, but does not describe. It predicts the statistics of outcomes with extraordinary accuracy, but it refuses to describe a hidden story unfolding behind the scenes. It does not tell us which path was taken, or what the electron was doing between its release and its detection. For many, this refusal felt like a failure. Physics, after all, had always prided itself on telling stories about mechanisms, about how one thing leads to another. The quantum wave seemed to break that tradition, offering results without narratives. And yet, the success of the approach was impossible to ignore. The predictions worked, not loosely, not approximately, but to a degree of precision unmatched by any previous theory. Measurements of atomic properties, magnetic effects, and energy levels lined up with the probabilistic predictions again and again, sometimes agreeing to more decimal places than anyone expected nature to care about. This combination of accuracy and restraint is part of what makes quantum mechanics so unsettling. It knows exactly what it is doing, but refuses to explain itself in familiar terms. To live with this, physicists had to accept a new kind of explanation, one that focuses on relationships rather than trajectories, on structures rather than stories, on the shape of possibility rather than the path of a particle. This shift also explains why attempts to force classical imagery back into the theory tend to fail. If we insist that the wave must represent a physical substance, we run into contradictions. If we insist that particles must have definite paths at all times, we lose the ability to explain interference. The quantum wave occupies a middle ground that resists both interpretations. It is not a wave of stuff, and it is not a list of hidden facts. It is a rule for how reality offers outcomes. Perhaps the most striking feature of this rule is how calmly it operates. There is no drama in the mathematics, no sudden leaps or special exceptions. The wave evolves smoothly, continuously, spreading and reshaping itself as conditions change. It is only when we intervene, when we demand a definite outcome, that the calm breaks. That moment, when prediction gives way to fact, is where the deepest puzzles begin to gather. Because while the wave tells us how likely different outcomes are, it does not tell us why only one of them actually happens. This is not a flaw in the theory's predictive power, it is a gap in its storytelling power. And that gap has been the source of debate, disagreement, and philosophical reflection for nearly a century. For now, it is enough to appreciate the wave for what it does remarkably well. It provides a clear, consistent, and extraordinarily accurate guide to the structure of possibility. It allows us to predict patterns without pretending to know more than nature is willing to reveal. As we rest with this idea, notice how the world feels both less rigid and more ordered at the same time. Less rigid, because individual events are no longer locked into predetermined paths. More ordered, because the overall structure remains stable, precise, and dependable. Reality, it seems, has traded certainty for consistency. And it is precisely at the moment when that consistency meets our demand for definite facts that the next puzzle quietly comes into view, the puzzle of measurement, the moment when a landscape of possibilities collapses into a single, undeniable outcome. There is a gentle tension that has been building beneath everything we've discussed so far. On one side, we have a calm, orderly picture of possibility, a wave that spreads smoothly, overlaps with itself, and predicts patterns with remarkable precision. On the other side, we have lived experience, a world where things happen once in one place, with no ambiguity at all. Sooner or later, these two pictures must meet. That meeting point is called measurement, and it is here that the quantum story becomes most delicate, not because the mathematics breaks down, but because our usual way of thinking does. Up to now, the wave of probability has behaved like a quiet guide. It has told us where electrons are likely to arrive, how often certain outcomes should occur, and how patterns form over time. As long as we remain in the realm of prediction, everything unfolds smoothly. The wave evolves calmly, reshaping itself in response to changes in the experimental setup. But the moment we actually look, when a detector clicks, when a dot appears on a screen, something abrupt happens. The wave no longer describes a spread of possibilities. It gives way to a single fact. An electron is found here, not there. One outcome occurs, and all the others, which moments ago were perfectly allowed, simply do not. This sudden transition is the heart of the measurement problem. Before measurement, the electron is described as being in many possible states at once. not in the sense that it is literally scattered across space as a physical cloud, but in the sense that multiple outcomes are genuinely possible. The description is broad, extended and uncertain in a very precise way. After measurement, that description becomes sharply focused. The electron is detected at one location. One value is recorded. The rest of the possibilities vanish from the story, and this happens every time. No experiment has ever observed half an electron arriving at two places. No detector has ever recorded a blurred compromise between outcomes. The result is always definite, clean, singular. This contrast is striking. The theory that governs the behavior of possibilities is smooth and continuous. The experience of measurement is abrupt and decisive. It feels as though two different rules are operating, one before measurement and another after. Physicists often describe this transition using the word collapse. It is said that the wave of possibility collapses into a single outcome when a measurement is made. But it is important to hear that word gently, without imagining a physical explosion or a dramatic snap. Collapse is not something we see happen. It is a way of speaking about the change in description. Before measurement, we use a language of possibilities. After measurement, we use a language of facts. The puzzle lies in how, or whether, these two languages connect. In everyday life, measurement is passive. It reveals properties that already exist. When you measure the length of a table, the table does not suddenly decide how long it is. The measurement uncovers a fact that was already there. Quantum measurement does not behave this way. When we measure an electron's position, the result is not merely revealed, it is selected. Among many allowed outcomes, one becomes real, and nothing in the probabilistic description tells us which one that will be. This does not mean that measurement creates reality out of nothing. It means that reality at this scale does not come with all its details pre-filled. Some aspects remain open until the moment they are forced into definiteness. This idea can feel unsettling, as though observation itself holds a strange power. But it is not the act of a human looking that matters. No consciousness is required. A detector, a screen, even an interaction with the environment is enough. What matters is that information about the system becomes definite and irreversible. Once an outcome is recorded, it cannot be undone. The electron has arrived. The dot is on the screen. The world has moved forward. What makes this especially puzzling is that the theory does not tell us why one outcome occurs instead of another. It tells us the odds. It tells us the distribution. But when the moment comes, it falls silent. This silence is not a failure of prediction. Over many trials, the theory performs perfectly. The statistics match, the patterns repeat, the wave of probability does its job flawlessly. The mystery lies in the single event. Why this dot, here, now? Why not one of the many other allowed outcomes? Quantum mechanics offers no answer to that question, and it does not pretend to. For some physicists, this was acceptable. The goal of science, they argued, is to predict what we can observe, not to provide a story behind every event. If the theory works, perhaps that is enough. For others, the lack of a deeper explanation felt incomplete. Not wrong, but unfinished. As if we were reading a beautifully written book that ends mid-sentence. This tension has never fully gone away. What is important, especially for our calm exploration, is to notice what the measurement problem is not. It is not a claim that reality is vague or ill-defined. It is not a suggestion that anything can happen. And it is not a sign that quantum mechanics is confused. On the contrary, the problem arises precisely because the theory is so precise. It draws a sharp line between the world of possibilities and the world of outcomes, without telling us how one turns into the other. That sharp line does not exist in classical physics. There, the world is always definite. Measurement merely uncovers what was already fixed. Quantum mechanics challenges that assumption at its core, and yet despite this challenge, the everyday world remains solid. Chairs do not flicker between positions. Baseballs do not land in multiple places at once. The puzzle is real, but it is also contained. As we sit with this idea, there is no need to resolve it immediately. Many of the greatest minds in physics have lived comfortably with this unresolved tension, focusing on what the theory allows us to calculate and observe, while acknowledging that something deeper may still be missing. In the next step of our journey, we will look more closely at the idea of collapse itself, not as a dramatic physical event, but as a story we tell to bridge two very different ways of describing reality. A story that works remarkably well and yet leaves us quietly wondering what, if anything, lies beneath it. As the idea of measurement settles, another quieter question begins to surface. When we say that the wave of possibility collapses, what do we actually mean? Are we describing a physical event that happens out in the world, like a spark or a snap? Or are we using a convenient piece of language to mark a change in how we talk about what is going on? This question has lingered at the centre of quantum mechanics for nearly a century, not because it blocks practical progress, but because it touches something deeply human. We want to know what is really happening, not just what we should expect to see. The word collapse is powerful. It suggests drama, a sudden fall, a decisive moment where something spread out is forced into a single point. It is easy to imagine the wave of probability shrinking instantly, as if squeezed by the act of measurement itself. But notice something important. No experiment has ever observed a collapse in motion. We do not see a wave shrinking. We do not detect a physical ripple racing across space, tidying up possibilities. All we ever see are outcomes, a click, a flash, a recorded value. Collapse, then, may not be a physical process we can watch unfold. It may be a way of speaking about a transition between two descriptions. Before measurement, we describe a system using probabilities. After measurement, we describe it using facts. In that sense, collapse functions like a punctuation mark. It signals that a sentence has ended, not that the letters physically rearrange themselves. It tells us when one mode of description stops being useful and another takes over. This view helps explain why the mathematics of quantum mechanics remains calm and continuous up to the point of measurement. The equations that govern the wave of possibility do not include a dramatic command to collapse. They describe smooth, predictable evolution. The abruptness enters only when we insist on reporting a single outcome. From this perspective, collapse is not something the system does. It is something we do. It is the moment we update our description to reflect the fact that a specific result has been obtained. But this raises a subtle concern. If collapse is merely a story we tell, does that mean nothing physical happens at measurement? Or does it mean that the physical process is real, but our language has not yet caught up? Different physicists have answered this question in different ways. Some have argued that collapse is not part of the physical world at all. On this view, quantum mechanics is a tool for organizing expectations. It tells us how to assign probabilities to outcomes. Once an outcome is observed, we simply update those probabilities. Nothing mysterious occurs in nature itself. The mystery lies only in our expectations changing. Others have been less satisfied with this answer. They point out that measurement involves real interactions. Detectors absorb energy, screens record impacts, information becomes stored in the environment. Something irreversible happens. And if something irreversible happens, perhaps something physical does take place that deserves a deeper explanation. What complicates the issue is that quantum mechanics handles both situations with ease. Whether you think of collapse as a physical event or as a change in description, the predictions remain the same. The statistics match. The experiments agree. The theory does not force a decision. This is where the phrase "shut up and calculate" quietly enters the story. It is often misunderstood as an expression of arrogance or dismissal. In practice, it reflects a kind of pragmatic humility. The calculations work extraordinarily well. They guide experiments, technologies, and discoveries with unmatched precision. Perhaps some argue that is enough, but even those who adopt this attitude often admit that it leaves an itch unscratched. He sensed that something important is being set aside rather than resolved. The discomfort does not come from confusion about the mathematics. It comes from the gap between two statements that both seem true. On one hand, the wave of possibility evolves smoothly and predictably. On the other hand, the world we experience is made of definite events. Bridging those two statements requires more than calculation. It requires interpretation. One way to ease the tension is to notice how often we already accept similar shifts in description. Consider a weather forecast. Before a storm arrives, we speak in probabilities. There is a chance of rain, a likelihood of wind. After the storm passes, we speak in facts. It rained. The wind blew. The forecast did not collapse in a physical sense. Our description changed because the uncertainty was resolved. The quantum case is more radical because the uncertainty is not merely practical, it is fundamental. But the pattern of description has a familiar rhythm. Prediction gives way to record. Possibility gives way to history. Seen this way, collapse becomes less like a mysterious force and more like a boundary between two ways of speaking. It marks the point where asking what might happen stops being useful and asking what did happen takes over. This does not mean that all questions disappear. It simply means that some questions may be ill-posed. Asking what the electron was really doing before measurement may be like asking where a storm was before it formed. The question assumes a structure that does not exist in the same way. For some listeners, this way of thinking feels unsatisfying. It seems to dodge the issue, replacing explanation with restraint. For others, it feels honest. It acknowledges the limits of what can be said without pretending those limits are flaws. What is striking is that quantum mechanics leaves room for both reactions. It does not demand a single philosophical stance. It allows different interpretations to coexist, all using the same mathematical core, all making the same predictions. This coexistence is unusual in physics. Typically, competing interpretations lead to competing predictions, and experiments decide between them. Here, the experiments remain silent. They confirm the mathematics, but they do not choose a story. This silence can feel frustrating, but it can also feel strangely peaceful. It suggests that reality may not owe us a narrative that fits neatly into human intuition. It may only owe us consistency. As we move forward, this perspective will help us understand why the measurement problem remains open without being paralyzing. It is not a crack in the foundation of science. It is a window into the limits of explanation. In the next part of our journey, we will step back from the microscopic world and look around at the one we inhabit every day. We will ask why, if quantum mechanics governs everything, chairs remain solid, baseballs follow predictable arcs, and the world feels so comfortably classical. The answer will not erase the mystery, but it will help us understand why the mystery stays hidden, whispering softly beneath the surface rather than shouting its presence in our daily lives. After spending so much time in a world of probabilities and unresolved questions, it feels natural to glance back at the room around you and wonder how any of this can be true. The surface beneath you feels solid. Objects stay where you put them. When you throw a ball, it follows a smooth arc and lands in a predictable place. There are no shimmering patterns of interference appearing in mid-air. no signs that the everyday world is quietly wavering between possibilities. If quantum mechanics governs everything, why does daily life feel so thoroughly classical? This question is not a distraction. It is one of the most important bridges between the strange behaviour we have been exploring and the familiar world we inhabit, and the answer begins with something surprisingly simple: scale. Consider again the interference patterns formed by electrons. They emerge because the probability landscape spreads out widely enough for different possibilities to overlap and combine. The wave of likelihood is broad, delicate and sensitive to small changes in the setup. Interference appears because there is room, both in space and in possibility, for alternatives to coexist. Now imagine replacing an electron with a baseball. A baseball has mass, a lot of it, compared to an electron. It also interacts constantly with its surroundings. Air molecules collide with it. Light bounces off its surface. Thermal vibrations ripple through its structure. Every moment it is being gently but relentlessly jostled by the environment. If we were to describe a baseball using the same language of probability, its landscape of likelihood would be astonishingly narrow. So narrow that, for all practical purposes, it collapses into a single path almost immediately. The range of possible positions is squeezed so tightly that there is no room for overlapping alternatives to interfere. In other words, the baseball's probability map hugs a classical trajectory so closely that it becomes indistinguishable from certainty. This is not because the baseball is exempt from quantum rules. It is because those rules play out in a way that leaves no visible trace at large scales. The patterns are still there, in principle. They are simply drowned out by the sheer number of interactions taking place. Think of it like trying to hear a whisper in the middle of a busy street. The whisper exists. It carries information, but it is overwhelmed by traffic, footsteps, and voices. The noise does not destroy the whisper, it hides it. The environment does the same thing to quantum possibilities. Every interaction between an object and its surroundings spreads information outward. Tiny correlations form between the object and countless particles in the environment. These correlations rapidly entangle the object's behaviour with the rest of the world, effectively locking in a particular outcome. As a result, the delicate overlap required for interference disappears almost instantly for large objects. Not because the rules change, but because the conditions for seeing their effects are no longer met. This is why baseballs do not produce interference patterns when thrown through open space. Not because they are classical at heart, but because their quantum behaviour is tightly constrained by their environment. Their probability landscape is squeezed into a narrow channel that looks, feels, and behaves like a definite path. Importantly, this explanation does not invoke consciousness. No observer needs to watch the baseball. No mind needs to be involved. The environment itself plays the role of an ever-present witness, constantly recording information and making outcomes effectively irreversible. This distinction matters because it prevents a common misunderstanding. The quantum to classical transition is not about awareness, it is about interaction. It is about how quickly information spreads and how thoroughly possibilities become distinguished from one another. When interactions are rare and carefully controlled, as in the case of isolated electrons, quantum patterns can survive long enough to be seen. When interactions are frequent and uncontrollable, as in the case of everyday objects, those patterns are suppressed almost immediately. This perspective also helps us understand why classical physics works so well in its domain. It is not wrong, it is incomplete. It emerges naturally from quantum rules when conditions favour stability and predictability. Classical trajectories are not fundamental features of reality. They're effective descriptions, approximations that become extraordinarily accurate when quantum uncertainty is confined to scales far smaller than anything we can measure directly. This idea can feel strangely comforting. It suggests that the world we experience is not an illusion or a mistake. It is a robust outcome of deeper laws operating in a particular regime. Quantum mechanics does not undermine everyday reality. It explains why everyday reality is as stable as it is. At the same time, it reminds us that this stability is conditional. Under carefully controlled circumstances, when interactions are minimized and systems are isolated, the underlying quantum nature can re-emerge. This is why interference experiments with larger and larger molecules continue to fascinate physicists. They test the boundary where the whisper becomes just loud enough to hear again. As you rest with this idea, notice how it softens the apparent divide between the quantum and classical worlds. There is no sharp boundary, no sudden handoff from one set of rules to another. There's only a gradual fading of visible quantum effects as systems grow larger and more entangled with their surroundings. The baseball follows its arc not because it is immune to quantum behavior, but because that behavior has been averaged, suppressed, and hidden by the environment. The same rules apply at every scale. They simply express themselves differently. This understanding also prepares us for the next step in the story. If the environment plays such a powerful role in shaping what we see, then understanding how it does so becomes crucial. There is a name for the process by which quantum weirdness fades into classical familiarity. It is not collapse. It is something quieter, subtler, and often misunderstood. As we move forward, we will explore this process in more detail, not as a magical eraser of uncertainty, but as a natural consequence of interaction. A process that explains why the quantum world whispers beneath our feet, rather than shouting its presence in every step we take. The idea we just explored leaves behind a lingering curiosity. If the environment plays such a powerful role in shaping what we see, then it deserves a closer look, not as a background detail, but as an active participant in the story. This is where a concept with an intimidating name enters gently, almost shyly into the conversation. That concept is decoherence. Despite how technical it may sound, decoherence is not a dramatic event. It does not involve sudden jumps, sharp collapses, or anything that feels explosive. In fact, its defining feature is how quietly it works. Decoherence is the process by which quantum possibilities lose their ability to interfere, not because they vanish, but because they become entangled with the environment in ways that make their overlap practically impossible to observe. To understand this, it helps to return to the image of overlapping possibilities. Interference depends on alternatives remaining delicate and coordinated. The wave of likelihood must be able to overlap with itself cleanly, preserving the subtle relationships that allow peaks and valleys to form. Any disturbance that scrambles those relationships weakens the pattern. The environment is full of such disturbances. Every interaction between a system and its surroundings spreads information outward. A stray photon bounces off an object. A molecule of air brushes past. A tiny vibration ripples through nearby matter. Each of these interactions leaves a faint record of what the system is doing. None of them, on their own, is decisive, but together they accumulate with astonishing speed. As these interactions multiply, the different possibilities that once overlapped cleanly begin to diverge. Each alternative becomes correlated with a slightly different state of the environment. One possibility leaves one set of traces, another leaves a subtly different set. Over time, these traces spread so widely that the alternatives can no longer recombine. Their interference fades away. This fading is decoherence. It is important to notice what decoherence does and does not do. It does not select a single outcome. It does not answer the question of why one result occurs rather than another. The wave of possibility does not suddenly shrink into a point. Instead, the alternatives become effectively isolated from one another, like branches of a tree growing farther apart as they extend. From the inside, it looks as though the weirdness has disappeared. Interference patterns vanish, superpositions become unobservable. The system begins to behave in a way that aligns with classical expectations. But underneath, the full structure of possibilities is still present. It has simply been dispersed into correlations with the environment, spread so thinly and so widely that it can no longer be accessed or recombined. This distinction matters because it prevents a common misunderstanding. Decoherence is not the same as collapse. Collapse is a way of talking about the appearance of a definite outcome. Decoherence is a physical process that explains why quantum interference becomes invisible in realistic conditions. You can think of decoherence as a kind of diffusion of possibility. The delicate patterns that require isolation to survive are gradually washed out as information leaks into the surroundings. The patterns are not destroyed, they are diluted beyond retrieval. This helps explain why the classical world is so robust. It is not that quantum behavior switches off at large scales. It is that the environment enforces a kind of stability by constantly monitoring and recording interactions. Not consciously, but relentlessly. The timescales involved are astonishingly short. For everyday objects, decoherence can occur in a fraction of a second. By the time you could even think to observe an interference pattern, it has already been erased by countless environmental interactions. This is why quantum experiments require such careful isolation, ultra-high vacuums, extreme cooling. Shielding from stray radiation, every effort is made to slow decoherence just enough to allow quantum effects to remain visible. When these efforts succeed, the results feel almost magical. Interference reappears, superpositions persist. The whisper becomes audible again. But the moment isolation weakens, the environment resumes its quiet work, and the classical world reasserts itself. Decoherence also explains why the transition from quantum to classical feels smooth rather than abrupt. There is no single threshold where quantum rules suddenly stop applying. Instead, there is a gradual fading of visible quantum effects as interactions increase. Small systems in isolation behave quantum mechanically. Large systems embedded in complex environments behave classically. This perspective removes the need for a mysterious dividing line between the microscopic and macroscopic worlds. The same rules apply everywhere. What changes is the degree of entanglement with the environment. It also clarifies why the measurement problem remains unresolved. Decoherence explains why we do not see superpositions in everyday life. It does not explain why we see one outcome rather than another. It tells us why alternatives stop interfering, not why one becomes real. This limitation is not a weakness. It is a sign that decoherence is addressing a different question. It answers how classical behavior emerges from quantum rules, not how reality chooses a single history. In this sense, decoherence is a bridge, not a destination. It connects the strange behavior of isolated quantum systems to the stable world of experience, without pretending to solve every philosophical puzzle along the way. As you let this idea settle, notice how it changes the emotional tone of the quantum story. The weirdness does not feel like a flaw or a failure. It feels like a delicate feature that requires special conditions to reveal. The classical world is not a lie. It is a natural outcome of constant interaction. This understanding also sets the stage for what comes next. If quantum behavior can spread across systems through entanglement, then the environment itself becomes part of the story. not just as a suppressor of weirdness, but as a medium through which correlations extend. In the next phase of our journey, we'll follow those correlations outward into a realm where connections persist across distance in ways that defy classical intuition. A realm where the quiet language of probability we have been exploring begins to speak across space itself. Up to this point, the story has unfolded gently along a single thread. We've followed one particle at a time, watched possibilities spread and fade, and seen how the environment quietly hides quantum strangeness from everyday view. Now that thread begins to branch. Not in a dramatic way, but in a way that feels almost intimate. Because the quantum world is not only strange in how single particles behave, it is even stranger in how particles relate to one another. Imagine two particles created together in a single event. They move apart, drifting in opposite directions, carried away by the normal flow of space. As distance grows between them, everything about common sense tells us they should become independent. Separate objects, separate stories. In the classical world, this is exactly what happens. Once two objects part ways, whatever happens to one has no immediate bearing on the other. Their connection fades with distance until it becomes nothing more than a shared memory of a past encounter. Quantum mechanics quietly refuses to follow that script. In certain situations, two particles remain linked in a way that cannot be reduced to shared history or hidden coordination. Their properties are not assigned independently. Instead, they are defined together as parts of a single, extended description. This connection is called entanglement. The word itself can sound dramatic, but the idea can be approached very gently. Think of a pair of gloves placed into two boxes. One box is sent to one side of the world, the other box to the opposite side. You do not know which glove is in which box. When you open one box and see a left glove, you instantly know the other box contains the right glove. There is no signal sent, no message transmitted, just knowledge revealed. This glove analogy captures something important, but it also hides something crucial. In the classical case, each glove had a definite identity all along. The uncertainty was only in your mind. In the quantum case, the situation is more subtle. The properties of the particles are not fixed in advance. They become definite only when measured, and they do so in a coordinated way. It is as if the universe postpones assigning individual answers until the moment a question is asked, and then ensures that the answers fit together perfectly, no matter how far apart the particles may be. Another way to picture this is as a synchronized dance. Two dancers begin moving together, then drift onto separate stages. They can no longer see or hear one another, and yet, when the music resumes and each dancer moves, their steps remain perfectly correlated, not because one sends instructions to the other, but because they are following a shared choreography written into the structure of the performance itself. Entanglement works like that choreography. It is not communication. It does not involve signals travelling back and forth. Nothing moves faster than light. Instead, it is a relationship embedded in the description of the system as a whole. This distinction matters deeply because it protects one of the most cherished principles of physics. Information cannot be sent instantaneously across space. Entanglement does not violate this rule. You cannot use it to send messages. You cannot use it to control distant outcomes. The correlations appear only when results are compared later. And yet, the correlations are real. They are stronger than anything classical physics can produce. When entangled particles are measured, the outcomes line up with one another in ways that cannot be explained by assuming that each particle carried pre-assigned answers from the start. No matter how clever the hidden explanation, it falls short. The statistics simply do not cooperate. This is where intuition begins to strain. We are used to thinking of your objects as having their own properties, independent of the rest of the universe. Entanglement suggests that, at a fundamental level, this independence is an approximation. In some cases, the universe insists on describing systems as wholes, not as collections of separate parts. Importantly, this does not mean that everything is entangled with everything else all the time in a way that overwhelms experience. Decoherence, which we explored earlier, quickly hides most entanglement from view by dispersing it into the environment. What remains visible are stable, classical relationships. But in carefully prepared experiments where interactions are controlled and isolation is maintained, entanglement stands out clearly. And when it does, it challenges one of the deepest assumptions we carry about reality: that separation in space implies separation in being. The discomfort many people feel when first encountering entanglement comes from trying to force it into a classical mold. We want to imagine signals, influences, hidden messages travelling secretly across space. But entanglement does not fit that picture. It is quieter and in some ways more radical. Nothing travels, nothing jumps, nothing is exchanged. Instead, the universe simply refuses to treat the two particles as fully independent entities. Their properties are defined together, even when they are far apart. This realization does not require us to abandon realism or embrace mysticism. It requires something more modest, but also more challenging. It requires us to accept that our everyday way of carving the world into separate objects may not reach all the way down to the foundations of reality. At the quantum level, relationships can be as fundamental as things. As you rest with this idea, notice how it shifts the emotional tone of the story. The quantum world no longer feels merely unpredictable or fuzzy. It feels relational, structured, carefully coordinated in ways that do not rely on force or communication, but on shared description. This sets the stage for a deeper confrontation with classical intuition, because if entanglement is real, then there must be a precise sense in which the universe allows correlations that no classical explanation can reproduce, and if that is true, then we can test it. In the next step of our journey, we will meet the thinkers who recognized this challenge and turned it into a question that experiments could answer. A question that asked very simply whether the classical picture could be repaired, or whether it had finally reached its limit. For now, allow the image of entanglement to settle gently, not as something spooky or threatening, but as a reminder that reality may be woven together more tightly than distance alone would suggest. A quiet connection, written into the fabric of possibility itself. As entanglement settles into view, it naturally invites a challenge. Not a loud objection, but a careful one, raised by someone who understood the stakes better than almost anyone else. If the quantum world truly allows such deep correlations across distance, then something essential about our picture of reality must give way. And for one physicist in particular, that price felt too high. That physicist was Albert Einstein. Einstein was not hostile to quantum mechanics. In fact, he helped build many of its foundations. What troubled him was not its success, but its implications. He believed deeply that the world should be intelligible, that physical systems should possess definite properties, whether or not we choose to measure them. Probability, in his view, was a sign of incomplete knowledge, not an ingredient of reality itself. Entanglement seemed to threaten that conviction. In a famous thought experiment developed with collaborators, Einstein imagined two particles prepared together and then separated by a great distance. According to quantum mechanics, measurements performed on one particle would be correlated with measurements performed on the other, even when the measurements were chosen freely and performed far apart. Einstein found this unacceptable, not because it violated mathematics, but because it seemed to violate a principle he held sacred, that nothing real should depend instantaneously on something happening elsewhere. He famously referred to this possibility as spooky action at a distance, not as an insult but as a warning. If quantum mechanics were correct in this sense, then either information was travelling faster than light, or the particles did not possess definite properties prior to measurement. Both options felt deeply wrong to him. Einstein's response was subtle. He did not claim quantum mechanics was useless. He suggested it was incomplete. Perhaps beneath the probabilistic description, there existed a deeper layer of reality, a hidden structure that restored definiteness and locality while reproducing the observed statistics. This was not a wild speculation. It was a carefully framed challenge. On the other side of this debate stood Niels Bohr, whose approach to physics was markedly different. Bohr did not share Einstein's insistence that reality must conform to classical intuitions about objects and properties. For him, quantum mechanics was not describing a strange world badly. It was describing a strange world accurately. Bohr's response emphasized limits rather than failures. He argued that concepts like position, momentum, and spin do not have meaning independent of measurement. They're not properties waiting to be revealed. They're outcomes that arise within specific experimental contexts. From this perspective, Einstein's demand for hidden definiteness was misplaced. The quantum world was not incomplete. Our classical expectations were. This disagreement was not merely philosophical. It shaped how physicists thought about what questions were worth asking. Should physics aim to describe what exists independently of observation? Or should it focus on the relationships between preparation, measurement, and outcome without insisting on an underlying story? For decades, this debate remained unresolved. Both sides could claim coherence. Both could reproduce the same experimental predictions. There was no obvious way to decide between them using observation alone. Then, quietly, a new idea emerged. In the mid-20th century, a physicist named John Bell realized something profound. If Einstein's vision of hidden definiteness were correct, then there would be limits to how strong quantum correlations could be. Those limits would reflect the constraints of classical intuition, dressed up in more sophisticated clothing. Bell derived a set of conditions that any theory preserving both locality and pre-existing properties would have to satisfy. These conditions did not require knowing the details of the hidden theory. They simply followed from the assumptions Einstein cared about. Quantum mechanics, on the other hand, predicted correlations that exceeded those limits. This insight transformed a philosophical debate into an experimental one. If the world obeyed Bell's limits, then Einstein's intuition could be preserved. If it did not, then no classical style repair would suffice. Over time, experiments were devised to test these predictions. They were careful, they were repeated. They closed loopholes one by one, and again the results aligned with quantum mechanics. The correlations were stronger than any classical explanation allowed. This did not mean that signals were travelling faster than light. That principle remained intact. What failed was the idea that distant systems could always be treated as having independent pre-assigned properties. In a gentle but decisive way, the universe answered the question Einstein had posed. Not by siding against him personally, but by showing that classical intuitions, no matter how refined, were not broad enough to capture what was happening. This moment marks a quiet boundary in our understanding. Beyond it, familiar categories begin to lose their grip. Objects are no longer guaranteed to carry complete descriptions of themselves. Separation in space does not guarantee separation in description. And yet, nothing chaotic or lawless emerges. The correlations follow precise rules. The mathematics remain stable. The predictions remain accurate. What changes is not the reliability of physics, but the shape of the stories we tell about it. Bohr's caution begins to make more sense here. Perhaps insisting on classical pictures was never the right goal. Perhaps the task of physics is not to preserve intuition, but to refine it. This does not mean abandoning the desire for understanding. It means accepting that understanding may take forms unfamiliar to everyday experience. That intelligibility does not always look like mechanical explanation. As you let this debate rest, notice how it reframes the discomfort of quantum mechanics. The strangeness is not arbitrary. It appears exactly where classical assumptions are stretched beyond their natural domain. The universe does not mock our intuition. It simply declines to be confined by it. This realization prepares us for the final stretch of our journey, because once we accept that the mathematics works while the stories diverge, we are ready to explore those stories directly. Different ways of speaking about the same equations, different attempts to make sense of a world that behaves consistently even when it refuses to feel familiar. By now, a quiet realization has settled in. The mathematics of quantum mechanics works. It works with extraordinary precision. It predicts experiments with an accuracy unmatched by any other theory in science. And yet, when we ask what the mathematics is telling us about reality itself, the answers begin to diverge. This divergence is not a failure of physics, it is a sign of something unusual. We have one set of equations, one reliable formal structure, and multiple ways of understanding what that structure means. These ways of understanding are called interpretations. An interpretation does not change the predictions. It does not add new numbers or adjust outcomes. It offers a story, a way of translating the language of probability and measurement into a picture of what is going on behind the scenes, if anything is. One of the earliest and most influential stories is often called the Copenhagen interpretation. Its name is associated with the community of physicists around Niels Bohr, though it is less a single doctrine than a shared attitude. In this view, quantum mechanics is not a description of an objective world unfolding independently of observation. It is a framework for relating preparation, measurement, and outcome. The wave of probability is not a physical object. It is a tool for predicting results. Questions about what the system is really doing between measurements are treated with caution or set aside entirely. This approach can feel unsatisfying at first. It seems to evade deeper explanation, but its strength lies in its restraint. It refuses to speak where the theory itself remains silent. It focuses on what can be said clearly and declines to speculate beyond that. This attitude is often summarized somewhat bluntly as "shut up and calculate." Despite how harsh that phrase sounds, it reflects a pragmatic wisdom. The calculations work. They guide experiments, technologies, and discoveries, perhaps demanding more as a philosophical desire rather than a scientific necessity. Still, not everyone is content with restraint. Another interpretation takes the mathematics at face value and pushes it to its logical extreme. This is the many worlds interpretation, most strongly associated in modern discussions with Max Tegmark and others, who emphasize its conceptual simplicity. In this view, the wave of probability never collapses. It evolves smoothly and continuously at all times. When a measurement occurs, the universe does not choose a single outcome. Instead, all possible outcomes occur, each in its own branch of reality. From within any given branch, it appears as though a collapse has happened. You see one result, not many. But the mathematics itself does not single out a preferred outcome. It simply describes a branching structure, where different possibilities separate and no longer interfere. This idea can sound extravagant, even unsettling. a vast proliferation of unseen worlds feels like a heavy price to pay for avoiding collapse. But proponents of many worlds argue that it is, in a sense, economical. It adds no new rules. It takes the existing equations seriously and refuses to modify them. The discomfort arises not from mathematical complexity, but from emotional weight. We are unaccustomed to thinking of reality as branching in this way, yet, from this perspective, the strangeness lies not in the theory, but in our expectations. Between these two interpretations lies a wide landscape of others. Some introduce hidden variables, some modify the dynamics, some emphasize information rather than matter. What they share is an acknowledgement that the mathematics alone does not dictate a single story. This raises an important point. Disagreement among interpretations does not imply confusion about the physics. It reflects a deeper ambiguity about what counts as explanation. For some, an explanation must describe an underlying mechanism. For others, it is enough to provide a consistent framework that links preparation and outcome. These are different standards, and quantum mechanics happens to satisfy one more readily than the other. Physicist and philosopher David Albert has argued that refusing to ask what is really going on risks mistaking strangeness for understanding. A theory can be accurate yet conceptually incomplete. Precision alone does not guarantee intelligibility. At the same time, history offers a cautionary note. Many successful theories were once conceptually opaque, only later finding clearer interpretation as new ideas emerged. It is possible that quantum mechanics sits in a similar position, waiting for a deeper framework that has not yet been discovered. What makes the current situation unusual is how long it has persisted. For nearly a century, the equations have remained stable, while interpretations have multiplied. No experiment has yet been able to distinguish decisively between them. The math predicts. Reality complies. The stories remain optional. This coexistence can feel unsettling, but it can also feel quietly liberating. It suggests that nature may not privilege the kinds of narratives we instinctively prefer. It may operate according to principles that are consistent and reliable, even if they resist being woven into a single intuitive picture. From a certain angle, this is not a flaw but a clue. It hints that our classical habits of thought, shaped by everyday experience, may not be the right tools for grasping the deepest layers of reality. Just as Newtonian intuition had to be revised in the face of relativity, classical realism may need to soften in the face of quantum phenomena. As we pause here, notice how the tension has shifted. Early in our journey, the discomfort came from strange experimental results. Now, it comes from abundance. Too many coherent ways of thinking about the same successful theory. Too many stories that fit the same facts. This is not a sign of failure. It is a sign that we are pressing against the edges of understanding. In the final session, we will step back and look at the quantum story as a whole, not to resolve its open questions, but to appreciate its character, its accuracy, its discomfort, and its quiet invitation to remain curious without demanding closure. As our long, quiet journey through the quantum world begins to draw to a close, it is worth pausing to take in the shape of the story as a whole, not the details of any single experiment, nor the arguments of any one interpretation, but the character of the theory itself. What kind of understanding has quantum mechanics offered us after all this careful listening? The answer is surprisingly clear, even if it is not entirely comforting. Quantum mechanics is, by every practical measure, the most accurate theory ever devised. Its predictions have been tested again and again, across scales ranging from the smallest particles to the behaviour of materials and technologies that shape modern life. Lasers, semiconductors, medical imaging, atomic clocks, and emerging quantum machines all rest on its foundations. When the theory speaks in the language of probability, nature listens with astonishing fidelity. And yet, despite this unmatched success, a quiet unease remains. The unease does not come from errors or contradictions, it comes from restraint. From the way the theory refuses to answer certain questions, not because it cannot calculate outcomes, but because it does not supply a single, settled picture of what those calculations mean. Throughout our exploration, we have seen this pattern repeat. The mathematics describes smooth, evolving landscapes of possibility. Measurement yields definite outcomes without explaining why one outcome rather than another becomes real. Decoherence explains why strangeness fades from view without explaining why a particular history is experienced. Entanglement reveals deep connections without allowing messages or control. Interpretations offer stories, but no experiment chooses among them. At every turn, quantum mechanics delivers consistency, but withholds comfort. This combination can feel unsettling because it challenges a habit of mind that runs deep. We're used to thinking that understanding means seeing how things work, step by step, like gears in a clock. We expect causes to precede effects, objects to carry properties, and explanations to feel familiar once they are complete. Quantum mechanics disrupts that expectation. It suggests that reality, at its foundations, may not be organized around definite facts waiting to be uncovered. Instead, it may be organized around relationships, constraints, and probabilities that only crystallize into facts at specific moments. The world does not roll forward along a single pre-written script. It offers a structured range of possibilities and then commits. This does not make reality vague or arbitrary. The structure is precise, the rules are strict, the outcomes when viewed in aggregate are remarkably stable. What changes is our role as storytellers. We are no longer guaranteed a single narrative that feels intuitively satisfying. This realization invites a shift in how we think about explanation itself. Perhaps explanation does not always mean uncovering hidden mechanisms. Perhaps, in some domains, it means learning to live with limits. Learning where language reaches the edge of usefulness. Learning when to describe patterns rather than insist on pictures. This is not an admission of defeat, it is a recognition of maturity. Science has encountered such moments before. The transition from absolute space and time to relativity required letting go of deeply held intuitions. The transition from classical determinism to probability required rethinking causation. Each time the discomfort was temporary, even if the adjustment took generations. It is possible that quantum mechanics marks a similar moment, that we are still learning how to ask the right questions rather than waiting for the final answers. There is also a quieter, more generous way to view the situation. Quantum mechanics may be incomplete, not because it is wrong, but because it is young in conceptual terms. The equations arrived quickly, driven by experimental necessity. The interpretations followed more slowly, shaped by human imagination and philosophical preference. It may be that a deeper framework, one we cannot yet articulate, will one day make the current strangeness feel natural in retrospect. Or it may be that no such framework exists. That reality, at its deepest level, simply does not organize itself around the kinds of stories we are most comfortable telling. If that is the case, then quantum mechanics has already taught us something profound. It has shown us that consistency matters more than comfort, that the universe is under no obligation to match our intuitions, only to follow its own rules faithfully. This is not a cold conclusion. There is a quiet beauty in it. The quantum world, for all its weirdness, is not chaotic. It is not capricious. It is subtle, relational, and deeply ordered. It allows precision without certainty, connection without communication, and prediction without narration. It invites humility without demanding surrender. As you rest with this final thought, notice how the tension softens. There's no need to resolve every puzzle tonight. The questions can remain open, gently suspended, like possibilities that have not yet collapsed into answers. Reality, it seems, may not owe us clarity in the form we expect. It may not owe us a single story that feels complete and reassuring. But it does offer something else, something just as valuable. It offers consistency. Again and again it behaves in ways that can be described, predicted, and relied upon. Even when our intuition falters, the patterns hold. Even when the stories diverge, the mathematics remain steady, and perhaps that is enough. In the quiet space between certainty and mystery, between prediction and explanation, there is room for curiosity without urgency, room to wonder without needing to conclude, room to let the mind slow down, knowing that the universe will continue to do what it has always done, whether or not we fully understand why. Thank you for taking this journey through the invisible reality of the quantum world. Whether these ideas remain clear in your mind or begin to blur softly at the edges, they have done their work. The story has unfolded, the patterns have been traced, and now, gently, it is time to rest.